I think some people are still asking for the passcode. Just give me a second. Hello. So good evening, everyone, and welcome to the online interactive lecture series that we have been organizing now for many months. And today we have a very, very interesting lecture, that lecture which, of course, not only deals with the physics, but also deals with probably one of the biggest problem of the future generation, namely the energy. So this is aptly titled as Simulating Sun on Earth, the ITER project. This talk is going to be given by Mr. Ujjwal Baruah, who is the project director of ITER India. And, we have had an outreach, I would say, drive in 2019, which is called Vigyan Samagam, and there were major 8 mega science projects of this country has participated in this particular outreach expo, which was conducted by DST, DAE, and NCSM. And the ITER project was one of the biggest, I would say, center of attractions during this period, for the fact that, as it is said often, this is one of the biggest challenges for our civilization. The way to to design such a big project and running. And also it says this is kind of a way to new, clean, safe, and nearly unlimited energy. So there's lots of things at stake, and this is probably one of the biggest project ever undertaken by a set of scientists and engineers. And to talk to you about that such a wonderful, or I would say challenging project, as I said, we have Mr. Ujjwal Baruah, who is the project director of ITER-India, and of course he's from Institute for Plasma Research, Gandhinagar. ITER-India is the responsible agency for implementation of ITER contributions, Indian contributions to ITER. And Mr. Baruah is a master's in electrical engineering from IIT Madras, and his personal research interests are in the area of high power neutral beam systems, electrical power converters, and high and ultra high voltage systems used for heating and current drive systems in fusion research. Under his stewardship, ITER-India is actively engaged with Indian industries for development of very complex engineering systems, which I'm sure you will see and enjoy how big these systems are, meeting the standards required for the ITER project. Okay, so with those few words about today's speakers and very exciting lecture that you're going to hear today, now I'll pass on the platform to Ujjwal for his lecture.
Thank you, Satya, for your very wonderful introduction. Let me go to the screen share first before I. Okay. As you, Satya, has introduced you to the ITER project, this is one of the largest scientific projects and have the largest participation from all over the world. It is said that almost half the world population or their governments are involved in this project, and this project is being built. If you have looked at the ITER website, must have been aware that it is being built at the southern part of France. And this is a wonderful project, as sector has introduced. It is basically trying to harness fusion as a source of energy and for the future generations. You know that fusion has been elusive for people for a long time till now. But this is not so. When I go through the presentations today, you will probably realize the difficulties. And I have planned the discussion in this manner. I will not get into the details of anything because uh, as the first one in the series of lectures that might be you might be listening, I would like to introduce you to the why that we have chosen the right this kind of a machine to be built, because there are different other ways of doing the probably different other ways of doing the same things. I will also talk a little bit about the Indian tokamaks that we have. Then we go to the ITER project directly and talk more about the Indian contributions and the future prospects that lies in the ITER project for us. Satta, am I audible properly?
Yeah, your voice, if you could improve a little bit towards the end, just now it seems quite good. But
Oh,
I would request you to kind of maintain close to the mic, please.
thank you.
Yeah.
And unfortunately, my camera is not working today, so excuse me for that. Uh,
That's right.
well, let us start this. Uh, we are talking about simulating the sun. In fact, not only the sun. If you look at the night sky, you see uh, innumerable number of stars which are glowing, and our sun is one which uh, we see during the daytime, which gives us the day. And our sun actually is a fusion reactor. All our energy that we use in any forms, except probably the nuclear one, which comes from fission, breaking of atoms. Everything else comes from sun. Call it the fossil fuel, it is because of the sun. Uh, call it hydroelectric, call it anything else, solar energy, everything. Well, these all these suns, small sun like ours, all the number ones, number of those out in the billions of miles away, these are powered by fusion. And before I get into the next one, I would like to show you a small clip, which is a nice one, describes how this whole business of fusion started. How do you, when did we start learning about fusion and what it means to us? This video I have taken from the ITER website, and returning to my slides, as you can note that it is already almost 100 years since someone talked about fusion in the sun, and we are still trying. What is nuclear fusion? This is a basically joining two atomic nucleus to a bigger one. When we get a bigger nucleus as well as some energy. And since there is a little bit of a loss of mass when two nucleus joins, we get that part as energy. And but how do you do that? The nucleus, as you know, is at the core of the core. The protons and neutrons will be there, but then it has a huge surge. All the surges are surrounded around that. It will not allow another nucleus to approach it quickly. There will be strong repulsion. But then someone found it out that they, apart from the strong nuclear force, this nuclear the repulsion will go only up to a certain point. When you bring something from a distance, there will be electrostatic force, which will be a repulsion, but then strong nuclear force at a very close distance will overtake at some point, maybe around 5 femtometer, and then there will be collapse onto each other. And but then you need to cross the barrier. You need to cross the barrier. It is just like you have to go up and up and up the hill before you can jump down. That much of energy need to be gained for any by any approaching nucleon. And for deuterium tritium pair, this is around 0.1 MeV. How did you find this number? Well, this is not a very new number. It is the number, a series of experiments conducted by Lord Rutherford and his team using accelerators. They have actually worked out all these numbers, how this fusion occurs, what is the energy required to do fusion. And our sun actually burns hydrogen. It burns 4 hydrogen atoms to fuse and get 1 helium and some energy. This actually it starts with 6 hydrogen and 2 hydrogen are given out at the end. It also produces neutrinos, gamma rays, positrons, and many other things. So this is possible in sun. It is because sun is a massive a body. A lot of gravity is there, and it keeps all the nucleuses, all the atoms in it together. It has all the energy also. It has also the time to react to each other. Here I will go to another video which quickly shows how this solar fusion is slightly different from what we are trying to.
The fundamental currency of our universe is energy. It lights our homes, grows our food, powers our computers. We can get it lots of ways: burning fossil fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have virtually limitless free energy. Is there a way we could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very fast. In this context, very fast means very hot, millions of degrees. Stars cheat to reach these temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant, the fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we wanted to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place. These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest temperature gradients in the known universe. The second type, called inertial confinement, uses pulses from superpowered lasers to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse. In fact, one of the most powerful lasers in the world is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like them around the world are today just experiments. Scientists are still developing the technology.
In the beginning of the universe, the time is exit or not.
It costs
So
more
how?
energy to do the
Can
experiments
you
than they
explain this,
produce in fusion.
please?
The technology has a long way to go before it's commercially viable, and maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth. But if it gets there, it will be so efficient that a single glass of seawater could be used to produce as...
Did anyone ask something?
Yeah, I think there was a question. Raghav Manchanda, do you want to ask a question? Okay, Ujjwal, we can go ahead. Maybe.
Okay.
That in the beginning of the universe, the time is exit or not.
Sorry, repeat.
That in the beginning of the universe, the time is exit or not. Beginning, sir, शुरुआत में मतलब.
Time
In
is
the beginning of the universe, the time is exit or not. Time is
exact.
exit or not.
as much energy as burning...
You are saying exact.
Sir, I am saying that in the beginning of the universe, the time is exit. Exist or not. Exist or not.
Okay. Yes, it does.
Sir, how?
Hello.
Setup.
Yeah.
Shall I respond to that?
Yeah.
Yeah, thank you for your question. Actually, let us hold it for a while because we are not probably at the moment we are going in a different direction. See, we are trying to see how this fusion reaction that is happening in different places all around the universe, that is the stars, how we can try to do it in a manner, capture it, do it something in a controlled fashion and use it for humankind. This is slightly different than the fundamental question of whether time exists or something like that. If you can postpone this question for a later period, I will be happy.
Yeah, that's fine. Yeah, thanks.
Shall we go ahead?
Yeah, please, Ujjwal.
A barrel of oil with no waste to speak of. This is because fusion reactors would use hydrogen or helium as fuel, and seawater is loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons, called deuterium and tritium, are needed to make the right reactions. Deuterium is stable and can be found in abundance in seawater, though tritium is a bit trickier. It's radioactive, and there may only be 20 kilograms of it in the world, mostly in nuclear warheads, which makes it incredibly expensive. So we may need another fusion buddy for deuterium instead of tritium. Helium-3, an isotope of helium, might be a great substitute. Unfortunately, it's also incredibly rare on Earth. But here, the moon might have the answer. Over billions of years, the solar wind may have built up huge deposits of helium-3 on the moon. Instead of making helium-3, we can mine it. If we could sift the lunar dust for helium, we'd have enough fuel to power the entire world for thousands of years. One more argument for establishing a moon base if you weren't convinced already. Okay, maybe you think building a mini sun still sounds kind of dangerous. But they'd actually be much safer than most other types of power plant. A fusion reactor is not like a nuclear plant, which can melt down catastrophically. If the confinement failed, then the plasma would expand and cool, and the reaction would stop. Put simply, it's not a bomb. The release of radioactive fuel like tritium could pose a threat to the environment. Tritium could bond with oxygen, making radioactive water, which could be dangerous as it seeps into the environment. Fortunately, there's no more than a few grams of tritium in use at a given time, so a leak would be quickly diluted. So we've just told you that there's nearly unlimited energy to be had at no expense to the environment in something as simple as water. So, what's the catch? Cost. We simply don't know if fusion power will ever be commercially viable. Even if they work, they might be too expensive to ever build. The main drawback is that it's unproven technology. It's a $10 billion gamble, and that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses. Or maybe, when the payoff is unlimited clean energy for everyone, it might be worth the risk. Videos like this one take hundreds of
Well, I think I have taken the videos, chosen the videos in such a way that it all gives you the crux of the matter, at both the positives and the negatives. Let us move on to the slow one, which I will give you now. As you have understood from the videos, that fusion on Earth will be slightly different from what exactly it's going on, the way it is in the sun. Well, there are quite some fusion reactions which are interesting to us. There are others possible, but remember, all of them needs very high energy to start. So what we are more interested in at the moment is the first one, that is the deuterium and tritium, which can give us a helium molecule, helium atom, and a neutron, fast neutron of 14.1 MeV. Altogether 17 MeV energy is available from this reaction. And this is what exactly is being tried out or planned to be tried out in ITER. We are going to try to fuse deuterium and tritium. This is why this is because, as you can see from the curves here, the DT curves picture the much lower energy as compared to any other of them, any other reactions. And even here, that peaks around at 100 keV, but even that is not necessary actually. People, scientists have calculated that even if you have fusion cross sections of something around this value, 10 to the power -3 or something like branch, you will be still able to do prepare a power plant which can give you energy which is commercially viable and which corresponds to something around 100 million Kelvin. Well, now the question comes is how to hold this something at this temperature. So yet here comes in the question of plasma. At that temperature, everything will be plasma. In fact, it will not be solid, liquid, or gas. It will be plasma where you have a cluster of ions and electrons, and they respond to electric and magnetic field. And this is what has been planned in controlled fusion experiments all over the world. The main problem with the fusion to happen is we need to bring the plasma of a particular density it's a temperature, and keep it long enough. This whole idea is how much energy is created from the reaction, fusion reaction, that must be not be lost out before it heats up something else and continue the same reaction. So there are mainly two kinds of schemes are being worked out. One is the inertial confinement, which use either electrostatic or a beam laser beam and a target kind of a thing. Electrostatic fusion had lot of potential, thought to be having lot of potential in the 50s, but then it is still used as a neutron source. But it is definitely not found to be not suitable for power production. Beam target is having some other problems. It is more or less this technology used there is of military domain. So people do not do this very openly. Of magnetic confinement, there are different concepts, something like mirror concept, where you create a magnetic field so that it mirrors out the ions. And the other one is toroidal confinement. And this toroidal confinement thing is most important for us. This is a picture of a mirror magnetic trap, where you can see that the ions in the plasma, they will gyrate around the field lines and move around there. But then in practice, actually, it also get lost very quickly. There is another very fine concept is the stellarator, where you actually twist the vessel itself, twist the coils itself in such a way that it takes the same pattern as the natural motion of the uh, ion trajectory. But then manufacturing that to a bigger scale is extremely difficult. People are still working on that stream and giving useful results. The concept we are talking about is the magnetic bottle called tokamak. It's a Russian word which means a magnetic bottle. And this is found to be at the moment most promising. And this has been proven uh, uh, practically possible in a tokamak made in Russia in 56 or 57. And this concept is something like this. This vessel will have that number of toroidal field coils, which produces the basic magnetic field lines along which these ions will move. In the center, we have a central solenoid. It is basically considered as a primary of a transformer, the secondary being the plasma here. As soon as there is a potential induced in the central solenoid, the some part of it is transferred onto the plasma, and that keeps the current moving in the toroidal part. So it doesn't go really out of it. But if you look at this picture on the right, you know that this will not go according to the path of the field lines, and field lines itself will have perturbations because coils can be only discrete. This cannot be practically you cannot make a coil with magnetic surface which is ideal that is shown in the picture. So they will move around. So to control that movement also, you add some other coils like what we call the poloidal magnetic field coils. These coils gives the plasma the right stability. Well, and now the question comes it how this magnetic field will be created. This magnet would carry several tens of kiloampere current in a modern tokamak. Like ITER, it will carry some upwards of 50 kiloampere current. And this at this temperature, at this current, if you allow a copper to conduct, this either the size of the copper will be too large, or copper loss will be too high. So that is becomes useless. So most of the modern tokamaks, including ITER, use superconducting coils. It avoids the large losses, and it can be operated in long pulses in that case. Apart from that, there will be number of other coil systems to increase the stability of the plasma. Where there are actually this is the crux of the problem, that how to keep the plasma confined and controlled. You also need to heat up the plasma to take it to the fusion temperature. There is inductive heating, as I mentioned, this transformer action by the central solenoid. But then that central solenoid uh, is a basically inductive heating is fine, but then you can see the geometry, it will lose lot of its flux elsewhere. So it is not a very efficient one, and that is also a transient one. So the other way to heat up plasma is radio frequency heating, which is more or less like your microwave cooker. You launch radioactive heats either at ion cyclotron frequency or the electron cyclotron frequency, or the other is a brute force method, where you essentially inject energetic particles, energetic neutral particles, because magnetic fields are so high that no uh, particle having a charge will penetrate the plasma. You need to accelerate the ions to a certain velocity, then you essentially neutralize it, and then allow the neutral beam to get into the plasma. Then it will give the exchange the charge and with the ions and heat it up. You also need a lot of extra materials, because we are talking about temperature of 100 million degree. So that temperature is created inside the plasma, but of course this plasma density is not too large, but then plasma itself can lose to the walls. So you need very high temperature resistant material, not only on the walls of the machine, then you also need to take the gas out. So wherever it goes out of the tokama, that there you will have even more severe conditions. So what is the status as on today? In 1991, as you have noticed in the one of the videos, Jet tokamak, that is the in a European tokamak. It is again a collaborative project among the all European countries. They demonstrated that you can fuse deuterium and tritium successfully. And in 1996, they actually produced 16 megawatt of fusion power. But then remember, at that time, they could get an efficiency of heating power to the output power of 0.67 only. And now we are trying to build a ITER here, which is expected to give us a Q of 10. And the respective size of the two tokamaks, you can see. I will show you the same in another slide later. Here you can see that volume of plasma inside JEC was only 80 cubic meter. Now ITER is going much higher, 800 million cubic meter. So bigger the size of the plasma is, that an energetic ion actually stays more longer time inside the plasma and gives it more time to collide with other atoms, other ions that is around. So that gives a better chance of uh, producing a feasible nuclear chain reaction. Sorry, not chain reaction here, it's a fusion reaction. Well, when you talk about this, we have to also mention that we are also doing the similar experiments in India. We have two tokamaks. One is the Aditya tokamak, which is a machine with a resistive copper coil. It can give discharges up to 125 kiloampere of plasma for up to 300 milliseconds. Now we are doing a little bit of an upgrade and trying to make it shaped. You can see that in this diagram, all the plasma, none of these plasmas are round actually in shape. We are now talking about shaped plasma because our experiments in the past has shown that shaped plasmas and these shaped plasmas are more stable, more easier to control. We have another project of SST1 superconducting coils are used here for the toroidal and polydale field coils, but then we are still struggling with it to make it operational to the extent we want to. Coming back to ITER, as we said, this is a ITER is trying to attack some of the key problems of fusion, and out of that, the confine and control the plasma. This is where science and technology required for that, and doing it safely. That is the main target of ITER. It is not trying to resolve the rest of the problems of materials, but some of the materials, some of the concept of breeding fusion fuel, that is in one of the videos you have noticed that tritium is not a naturally occurring element on the surface of Earth. We need to produce it. That is discussed in the, that is also tried out, that will be tried out by, to some extent in ITER. And as a big project, it's a very big project. There are some statements which gives a objective, sets the objectives of the project, which talks about producing a 500 megawatt of fusion power up to 400 seconds. And when this is there, the input power will be 50 megawatt, and so the efficiency will be basically power amplifying factor is Q greater than 10. This is most important objective of ITER. Apart from that, it will continue to operate other forms of plasma up to 1000 second operation, up to 3000 second operation, and so and so. But that is only when the future will say. This is the other one is to show that this quite some technologies are proven here, and it will test tritium, and it will show that it is safe. This background is a checkered history. Actually, it started in 86 in a, it's a sort of a political project, you can say, between the US and USSR. Some of you may not have been born at that time, 1986. And then finally, the agreement was signed in 2006, and they established the project in France, Cadarache. And we have
Ujjwal,
7 parties. Yes.
Can I interrupt you?
Yes, sir, please.
There is a question on the Zoom chat.
Yeah.
Debashis Mondal. It says tokamak is surrounded by the superconducting magnet, where
Yes.
the gyrotrons are also surrounded by superconducting magnet. Will there be any effect on the gyrotron performance or vice versa due to different strengths of the magnetic field?
Well, this is, if you are talking about the gyrotrons that is used for high frequency heatings, these gyrotrons will be installed far away from the tokamak itself. And from there, the radio frequency wave, that is the 130, 170 gigahertz wave, will be routed from different buildings through a series of transmission lines. So this problem is not there in the present system. Basically, the gyrotron is far away from the it is basically in a different building as compared to the main building.
Okay.
Does that satisfy him?
I hope so.
Okay, fine.
Yeah, please.
Okay. So we are 7 partners. Actually, we are China, Europe, India, Japan, Korea, Russia, and the US. And you know, Europe is 28 nations. And the key parameters of ITER is this: major radius, that is the radius of this big plasma volume is 6.2 meter. Minor radius is 2 meter. That is the volume of the plasma, height of the plasma, you can say. The toroidal magnetic field will go up to 5.3 Tesla. Here, this plasma current expected is 15 megampere. We have provision for heating up to 73 megawatt, but then this is not always possible. With 50 megawatt, we expect to gain up to 500 megawatt of fusion output, which can go up to 400 seconds. And these walls, that is heat load on the walls, that will be limited to half a megawatt per meter square at the moment. Because, but that, remember, that is not good enough for a fusion reactor which produces power and connects to the electricity grid. This, as you have seen here, it is a gigantic things. It is too large. The machine itself some 30 meters tall and so that much of a wide. And to run all these things, there are the all around the places, there are a number of auxiliary systems will be installed. So some of these dimensions can be seen in the next few photographs. This is one of the TF coil. You can see the size of the TF coil and the people there. This is one part of the vacuum vessel sector. You can see the people standing in the platform there, and this is one of the sectors of the vacuum vessel that we have that has been built, and there will be 9 sectors like that. There will be 16 TF coils, and the key parameters, as I said, the okay, let me skip that these details because this will take time, except that I'll identify the cryostat here. This outer part, that white one you see here, that is the final volume which keeps the superconducting coils inside cool. This is a vacuum vessel that is made by India, which I will come to you a little bit later. These green coils you can see there, that is part of the central solenoid. These are the two things, and the orange one are the PF coils. Sorry, toroidal field coils. Well, this progress is making, it is making, I need to be short actually. I cannot go into details of any of these subjects. Let us go to the progress so far. There are two photographs here. One is 9 years back, and the other one you can see there are lots of things happening at the moment. And since ITER is a collaborative project, everyone chooses that they will build different components at different places and bring all over to ITER and assemble it. Again, this is better described by a small video again, which I would like to show you. This is made in India. Again, this is made in India. Indian supply again. This is part of the vacuum vessel. Gigantic tools used for assembly. And this is where the machine is. You can see the cryostat lower sections sitting there. Well, coming back, there is no more videos, but then I think the videos gives better picture than what I can explain to you. This assembly of this machine has started at the moment, and this formal ceremony was held on 28th of July. Yeah, Prime Minister sent a message, and the Indian ambassador there read it out. Uh, uh, then onwards, I go to the ITER India's contribution of. Uh, do you want to take me the question now, Sector? Raghav
You
Manchanda
can
has
go
given.
ahead. You can go ahead. I think you can finish this part.
Yes. Let me finish this. I'll come back to it. Don't worry. We are giving 10 packages to ITER. And there are a few pictures which will quickly go through what is the progress today. As you have seen that crash that is the biggest one actually, where is 29-meter tall and 28-meter diameter, just something like a 10-story building, height of a vacuum vessel here. And yes, this need to be done in a very precise manner. Just also the what you call the nuclear barrier, second confinement barrier for the ITER tokamak. Uh, you can see the walls here, and that a small gap in between, and then between that, we are installing the cryostat today from Indian colleagues. This lower part and this part, these two parts has been already installed in the site. We did this manufacturing plan of putting it into cut it into several pieces and building smaller pieces, taking there to the workshop which we created at the site. You can see the dimensions of the size. That this is one of the mock-ups that we did uh, of the lower part, and the size of the person and the size of the one part of it. You can size of the person and the part of the equipped sector. These were transported there and built into, it's basically a very heavy engineering, mechanical engineering job. It should excite the mechanical engineers if someone is listening. This is a part of the transportation. This you can see the very large in a ship. There are only few pieces can go at one time. This whole planning was not so easy in the beginning. And these two parts, you can see that these are already installed. This one part is unstored, which you could see in the video at around bobbins standing out in the field. This is when this lower cylinder was being transported by the crane here. That is at uh, for the pit to be installed there. This is being installed in the pit. As another view from that top level, it is installed there. Another one is where this lower cylinder, this part which is above the crash at base, it is being taken there for installation. And this is what we celebrated recent in the June, is the completion of manufacturing in Indian facility. That is L&T manufactured this for us in India at Hazira. Hazira was chosen because that is the only place from where the ship could take it very easily. Otherwise, road transport on India of these big species would have been extremely difficult. Apart from the cryostat, we also have the big package called cryo distribution and cryolines. It is all transfer of a lot of cryogenic fluids, which is actually supplied by a 75 kilowatt. It's a gigantic liquid helium plant that will cool all the superconducting magnets, that is the central solenoid, polarial field coil, toroidal field coils. And this, all the network coming from some 500 meters away will be transferred by cryolines and the distribution system. That is our package. There's a schematic of that. This plant itself is not delivered by us, but then from the here onward, all the lines up to the manifold here, these are the manifolds here basically, that tokamak itself will be lying here itself in this space. This was our package, and we are making some 70-80% progress till moment. There are quite few R&D and industrial learning, and one thing we are very proud that this is one area where India was not up to the mark to the world leaders at that point of time when we started the project, but then at the moment at least one Indian vendor, that is Messrs. Inox, they have qualified to do this kind of things, process pipe of or larger than 1 meter diameter and so and so. There are some of the view graphs from there. You can see that the cryogenic lines is getting ready for transport here, and you see that what goes inside the cryogenic lines. Careful welding, precise wrapping with insulating layers, and difficult. It's basically mechanical engineering job, cryogenic engineering job should be very much of interesting to many of our young colleagues who are in engineering of this kind. This is one test facility that we created in the India, ITER-India and Gandhinagar, to test this, qualify this system fully before we could take any risk. So that we do not get into problem in after installation at ITER site. This is one of the largest cold circulators that is supplied by us, but then not developed by us. Actually, it is a Japanese company who developed it for us. There are more of them, but again in the factory in India. These lines are being installed in the ITER site. At the moment, in fact, before that tokamak comes in, you can see a lot of lines, cryogenic lines installed by India, which prominently, if someone walks around the tokamak building. This is another component that is the coal box. Again, not delivered by us, but not made by us. we are trying to still develop these technologies. These are new areas where we need to see how we can accelerate our engineering R&D to meet the world standard again. There is another package, what we call in-wall seal blocks. Actually, if you recall the vacuum vessel is made of 9 sectors and it's a double wall vessel. There are 2 walls. It is and in between the walls, it is stuffed with a lot of iron blocks with a special iron having large component of boron, so that the neutrons which are coming out of the tokamak, which we are not using at the moment in ITER, basically, that is lost as a, and that should not be allowed to leave the main machine to the extent possible. These blocks are for that purpose. We have produced all the blocks that is given to us, and all these blocks has been uh, transferred to ITER organization, who in turn has given it to European and Korean manufacturers, who are stuffing them inside the vacuum vessel sectors as they are building it. You can see some of the blocks here. They are stuffing it. A large vacuum vessel sector, you can see that was seen in the video also. This is ready, and then after that it has been sealed with after welding at all from all sides. This is complete. The another system that we are giving to ITER is the secondary cooling system. That is the whole cooling water goes to the going to the different plants as well as the tokamak. If you see the ITER landscape, it is basically most of the equipments are cooling water related systems are installed now. This is the cooling tower that is seen from the picture, and all these equipments on the side are again cooling water pumping equipments. We have extensive cooling water system capacity of 500 megawatt and 1200 megawatt peak capacity, and several cooling towers, a lot of pipe networks and all other things. But then remember that all of these systems actually had a very specific requirements, either being a nuclear site, and French regulators did not know exactly what fusion is going to be. So they are little bit more cautious. So all different systems that is supplied from India, it is fully made in India system, again made by supplied by Messrs. L&T. Also, and they have several subcontractors. We are happy to say that many of the subcontractors like Kirloskar Pumps, like Paharpur cooling towers, they did quite some R&D to ensure that our equipments do not fail there in ITER for at least several years after we leave that site. So several new things were done in the system. Some of these are here, you can see. Again, this is exciting for the mechanical engineering students and the practitioners. A lot of pipe works in the ITER site being installed, but this is not done by India. The pipes are installed, given by us, installed by the European contractor. Cooling tower is a long vertical pump. It is being installed there. All these systems are tested here once, and that is tested there again. As I see that the big cooling tower fans are vibration tested here. It's not only for the operation of the fans, it is also important that it doesn't fall off during the transportation also, because that is by sea again. We are almost through with this all these 4 packages, but then these are the essentially required for on the priority basis by ITER by 2025, so that the first plasma operation can start. We have some other packages for which R&D is still going on. We have a diagnostic neutral beam package which accelerates ions up to 100 kilovolt and produce the neutrals, and this is installed in this position of the tokamak. And this is used only for diagnostics. Basically, it is not a very energetic beam, but it is used for helium S measurement. And the principle is basically, as I was telling, that is depicted here. First ionization, then neutralization, then separating the ions and allowing the neutrals to pass on to the tokamak. Certain test experiments are being done here. It's a large ion source, RF driven ion source. We have achieved a beam of 2 ampere, but remember we have to go up to 60 ampere of beam delivery. Another experiment which is slightly bigger.
Ujjwal, can I interrupt you?
Sure, please.
Yeah. So one question from Professor Vivek Datar.
Yeah.
So is the energy of neutrons used through neutron alpha reactions on boron? What fraction of neutrons are used to breed tritium from 6 lithium?
Well, that is actually a tiny fraction. At the moment, ITER does not have a full-fledged tritium breeding program. Tritium breeding will be done only in a small part of the uh, ITER machine. If I go back to one of the crash test slides, I can show you. Only a small fraction will be used for tritium breeding at the moment, actually. So you can see there are lots of ports here in the system. And of the many ports, all the ports are actually reserved for diagnostics or some other equipments. But only 2 ports of them, only this much and probably on one of them here, are reserved for tritium breeding experiment today. So a fraction of tritium used for actual breeding experiment is minimal. It is less than probably 1% at the moment. The rest of it will be lost in these in-wall seal blocks and then by water, because the in-wall seal blocks are stuffed without welding, and this whole blocks are actually immersed in water which is circulating. And this circulating water will also absorb the neutrons. And overall, ITER is not built for producing lot of neutrons at the moment, because that neutron operation will be much restricted towards the end of ITER's life. Before that, more stress will be on the stretching the plasma operation for longer period, uh, establishing 15 mega ampere and that kind of a plasma operation, controlling it the way we want to do. That is the basic focus of ITER, and go for a selected DT operation towards the end of its life, when it will go for tritium breeding. Yes, that is that. Shall I move on?
Okay, Ujjwal. Yeah, please.
Okay. Okay. Diagnostic neutral beam, as I said, it is we are establishing a full beamline here. Our target is to get 5 to 7 millirad at a 15-meter long, a 15-meter distance from the ion source. Many R&D has gone in the materials of this production of this itself, where we are collaborating with several institutes within the India. Some of the things are still under work in progress. These are grid plates of the one of the after precision machining of the grid holes for the answers. This is one of the vessels. This main vessel, basically, for the diagnostic neutral beam, is being installed in ITER-India lab at the moment. We have also the ICRF power sources, basically ion cyclotron radio frequency heating, which heats at the around 35 and 65 megahertz range. We are going to give 2.5 megawatt 8 sources, making up to 20 megawatt, and this is required for accessing the H mode of operation. That is what high stability mode of the plasma. This is again, we are giving the only the RF high power sources only, along with the power supply, which comes in a different package. And this is basically a big amplifier starting from a very low power at different stages. It goes up to the highest level. And the present technology gives a HPA, that is at the out of the HPA we'll get only 1.5 megawatt. So we'll combine these two branches of 1.5 megawatt outputs to get 2.5 megawatt continuously, and probably 3 megawatt as well. This is the design at the moment. One half of this system has been built basically and tested at 1.5 megawatt. This is a picture of that. We are also doing a lot of R&D and testing different components that need to go from India. But these are still being characterized. We also have to produce, give two gyrotrons, basically 1 megawatt source of 170 gigahertz operating frequency. ITER has 24 megawatt of heating power, but we are giving only 2 megawatt out of it, which is derived from gyrotrons. And then there also we are making the test facility here, because operating a source of that kind, again, that will be imported from Russia. Source itself. Operating and making it stably operated is not an easy affair. We are setting up the full test bench here. We are doing quite few diagnostic systems. Mostly our diagnostics, there are altogether more than 100 diagnostics in ITER, and spread over all the participating countries. Basically, bulk of it lies with Russia and the US. Europe does the next part, and we are doing 4 of them. And out of them is one is charge exchange recombination spectroscopy, uh, another spectroscopy of X-ray survey. We are also doing the edge imaging spectroscopy. And we are also doing something called electron cyclotron emission ECE diagnostics. And some of these are still at R&D level. And we need to also deliver a port plug, basically, that one of the port plugs we are delivering. This is under manufacturing at the moment. Doing some R&D on the ECE diagnostics here, which is works in a terahertz range actually. We are doing a lot of power supplies actually. This is where my competence lies actually. And we are doing a set of power supplies for the ICRS systems, for the ECRS systems, for the diagnostic neutral beam complete power supply systems. And a lot of these are actually produced in-house based on in-house technology that we developed and transferred to industry. Again, Indian manufacturers like Electronics Corporation, they are doing this using our technology. One of such power supplies, 95 kV, 75 ampere, has already been supplied to ITER. They are working in a test facility for a neutral beam. And some of these power supplies view graphs here. This lower one is actually the supply that we have supplied to a neutral beam test facility in Padua, Italy. Well, this is what I have to say about what is our deliverable. Now, probably I would like to go towards the concluding part, uh, which is more important for you. Basically, you can see the photographs of our colleagues working in ITER here. That was a photograph taken in probably last year, 1 year back. Uh, the objective of India joining the ITER program is to create the manpower in the R&D institution, both in the fusion. Basically, even the fusion is the key. But if you see the extent of engineering required for each of these equipments that we are supplying, and what we have access to from that is being delivered by other countries, those are key importance to Indian program. So this is the main objective. And as we get into the operations, at the moment we are talking over only the construction, and we'll get into operation starting in 2025. Probably in 2028 we'll get into serious operation of ITER, and that is the opportunity we need to have our academics and students do scientific experiments in ITER. This is most important part for us, and also the opportunity. And also we are probably going to do it with industrial help, so that industry also takes it forward to other areas. So this is what I told you already, that we'll start operation in 2025, but then actual operation of the machine for physics experiments will be available only in 2028. And 2032, we will go for a preparation for deuterium tritium operation. And 2035 onwards, it will get into DT operation, when we can see that whether the desired goal of reaching the sustained DT operation for 400 second, achieving that Q factor of 10 is possible or not. And meanwhile, there are good news that JET that we talked about in one of the slides, they are going for a DT operation. Of course, they do not go for a long pulse operation. They can go only up to 10 seconds, but their DT operations might be even shorter. They are going for a DT operations after a long time in this year, starting from March. So before I conclude, I must say that there is opportunities exist, and for the young researchers, young students, they need to take it forward in the future. This will be a wonderful machine built like CERN, which was built 50 years back, and experiments are never ending. It's creating new knowledge. This is the same thing will happen. We need to prepare, and at the moment, who are interested in working with ITER, they can also look for ITER intern student program, which is a very interesting program to attend to. They actually allow students for 3 years. Well, my concluding comments here. Sorry.
Okay.
Uh, so we'll get. I think it is all dream. I am giving you the dreams, but that I think this is what is important, that we keep dreaming and work hard to reach that, achieve that dream part of it. And India is committed. And as you can see, the government has already committed. So it's a very responsible position India has taken by working with ITER all the time. You can see some of these websites if you want more information, or write to us also. Thank you.
Thank you. Thank you very much, Ujjwal, for that very, very comprehensive and very exciting lecture on this gigantic project. Rightly put in, this is a source of future energy for all of us. And of course, one is looking at these long time scales that you projected, but it is a worth wait, because this is really something which everyone is looking forward to. We have only about 10 minutes for question answers. I would like to take a few questions which are waiting in the YouTube first before I come here. Let me, what is the efficient method to inject the particles inside a plasma chamber? This is a question from Abhinav Chaudhary.
Well, I think the most efficient is the neutral beam, because it directly transfers the energy of the particle to the plasma. And in ITER, they are planning to inject beams at 1 MeV. They will accelerate the ions in ion source up to 1 MeV. Then they will neutralize it. It is basically they will accelerate deuteriums there, which is for some other regions, I think it seems to be better than hydrogen. And they will, because that can penetrate deep into the plasma and launch the heating, all the power to the plasma. Whereas radio frequency sources, that ion cyclotron or electron cyclotron, they cannot penetrate the plasma, and then it is basically an indirect method of coupling. And a lot of it is reflected back from the plasma. But then the technology of 1 megavolt acceleration itself is not existing at the moment, and that is being tried out in a test facility, which is part of ITER actually, neutral beam test facility in Padua, Italy, where we are also participating.
Hello, sir. My
And
question also.
sorry.
Hello, sir. Raghamanchanda.
Yeah, just 1 second, please. Just 1 second, please.
Okay.
I think this is, I have covered this question.
Yeah.
So neutral beam is the most important thing to
Sure.
pursue.
There's one question from Uttam Goswami. Sir, is the energy released from fusion reaction? How is it collected from the tokamak and to grid? Is it the same way what we have in fusion reactor? Or I'm curious to know these technologies.
Well, I think at the moment we are actually only cooling the heat generated and taking it away in the cooling
Okay.
towers. That is the reason we are having such a big cooling tower and that kind of thing. In future, when we are talking about the using the energy for generation, probably the walls of the machine will have a special design and special material which can produce the steam, which will be used to run a generator and connect to the grid. This is what is being planned, and that is what is schemes are available, being designed by different people, but everyone is just waiting and watching the outcome from ITER, because that controlling the plasma itself is not that easy as on today.
Sure. I think there's this question about Gyratron, which you already answered, but please inform about the plan for development of 170 gigahertz Gyratron in India.
Well, I think at the moment we have not started this program as in a very serious sense. We are doing some theoretical work, of course, and probably everything cannot be done in our institute alone, because our main core focus is on controlling the plasma and so and so. And there are institutes like Seri Pilani we are working with, and definitely we will be interested if someone is interested to do serious work on this line, and we'll like to see how it goes, obviously. As on say, there is no firm plan, but then any plan is welcome. We can definitely try to push it forward.
One question I would like to take from Professor Vivek again. Which countries are involved in making the superconducting coils?
Well, superconducting coils are being made by Japan, Russia, China, US, and Europe. Left out is Korea and India. But it's also important that superconducting coils are one thing, but then superconducting strands, manufacturing of the superconducting strands itself is another area where actually all the parties, all ITER parties except India have produced it. That happened because India joined the program, the last partner, in 2005 end, that is the month of December. By that time, everything was shared between the parties, and we were left out without the scope of manufacturing the superconductors in India. That is a pity for us.
Okay. There are two questions. Okay, let me take this before we go to Raghav Manchanda. This is from Debashish. Say, I'm a research scholar at IIT Roorkee pursuing my thesis on gyrotrons. I would like to know in detail the opportunities for students, especially for PhD students, to visit ITER.
I think I have already addressed
Yeah,
that.
Sir, what happen if two neutrino and neutrino collide to
just
each other?
1 second, please.
Okay. Thank you.
Raghav, can you please wait?
Yes, sir. Yes.
Yeah, also please you have to ask questions which are relevant to this talk. Please, just hold on.
Okay, I think at the moment you can definitely write to us, and I would also suggest that you look at ITER's website, and they gives internees, and also for they offer a good postdoctoral fellowship.
Okay.
Since you are already a PhD student, I would suggest you attempt that. There are quite some interesting topics they offer. Directly working with ITER fronts. And for us, working with us, definitely you can write to us. We can see what are your interests, and accordingly we can try to see what can be done.
Okay, before we, just one last question from YouTube. This is more for the INO project than ITER, but this is a nice question. It says, what INO project can learn from ITER? For example, collaborating with industry, following quality requirements, and training of engineers and so on. So with your permission, maybe I'll try to answer this.
Please.
Ujjwal. So yeah, this is a nice question. Of course, all the mega science projects which we keep talking about requires a very large collaboration with not only with various institutions like what Mr. Ujjwal Baruah mentioned about, but also with industry, right? Just like ITER, of course, ITER is a much more, I would say, engineering intensive effort, maybe in proportion to INO, but nevertheless, we do have lots and lots of industries collaborating with us, and we can't really build such a gigantic experiment without collaborating with industry, and they making most of the crucial components, all of them within the Indian industrial community. So that is the first part. Of course, we also have to follow very strict quality requirements. Otherwise, the experiment cannot just be built together and meet the scientific goals of the experiment. And the third question about the training of engineers, INO has its own PhD program. I'm sure similar one to what Ujjwal mentioned for ITER. And we take both students from science and engineering background, and they work towards their PhDs, working on one or the other INO related problems, and then get their PhD. So there are about 45 to 50 students who joined INO, and out of which more than half of them are already passed out, and they're of course doing extremely well both in India and abroad. So that is the question from Karipudi Gopi. Okay, so we come to the last question on Zoom. I think, is he here right now? Raghav Manchanda, you want to ask a question?
Sir, what happens if two neutrino and neutrino collide to each other? Two neutrino particles collide to each other. What happens?
I think Shatta, you need to take this question.
I don't know, me or maybe if Professor Datar is there, maybe you can answer that.
Yeah, I mean, this question is not relevant to this talk at all,
Yeah.
because the neutrinos will escape. Even one neutrino will not interact, even if it is
Two
produced in beta decay of, let's say, tritium or some other radioactive isotope. This question is only relevant in conditions where there is a huge density of neutrinos and antineutrinos. That happens in supernova explosions. So you should read up some material on that. This is not relevant here.
Sir, one more question.
Just 1 second, Raghav.
Please direct it to the, I mean, let it be relevant to the talk, I think. The other questions you can write to, INO website. There is a mail given there if it is related to neutrinos. I think you ask questions related to this talk.
Okay, Raghav, please write to contact.us. I will in the on the chat I'm writing. So please refer to that and you can ask.
Sir, only PhD student can visit the INO lab.
No, these questions are all here. I've given the web page here. You please write. We will answer every question that is asked. Every mail that is sent, we will answer you. Okay? Yeah. There's one last question I just happened to see. This is from Siva Subramanian. Can you please ask this question, please? Okay. Or otherwise, I'll read for him or her.
Yeah.
Could you throw some information on China's HL2M tokamak reactor and the difference in design, goal, concept, and design?
Well, must say that China has a much bigger fusion program than we in India. And this is one of the tokamaks. They are running for some 20 years at the moment. This is also a superconducting tokamak. But the dimensions wise, it is much smaller. It is something like what you have seen in the Z or something like that. I have not tracked it fully whether it can go to deuterium tritium operation. I think it is not, because as soon as you go for DT operation, you need to take, it becomes a nuclear machine actually. You need to take follow several protocols for safety. But on the hydrogen plasma, they are definitely doing quite some good results turning out. They also have neutral beam injector. They also have RF heating, similar to. They also have the superconducting tokomers, similar to ITER. That's you can say that there are quite some useful physics can be done on machine, but definitely not used for producing power or doing real DT experiments. Does that answer that question?
Yeah, I hope so, because I was not able to kind of get the participant asking question themselves. But I guess
I
it.
see.
Okay. Just let me check if there are any questions. Yeah, I don't see any question. Of course, there's one question on the YouTube I answered on your behalf, but if you want to just say in one word, you can say that is India only supplying the equipment or also participating in the experiments and operations?
This is exactly I said.
Yeah.
At the moment, it is construction, and we are constructing like Europeans, like this Japanese. We are doing the R&D required for sending the equipments. And when the ITER starts in 2025 and seriously starts in 2028, we need to participate in large numbers in ITER experiments. This is what is the goal.
Okay.
And this belongs to you people, actually, younger people.
Yeah, the timelines are such that, of course, none of us probably will be there at that time. So with that, let me, on behalf of all of you, thank Ujjwal, Mr. Ujjwal Baruah, for
Thank you.
time to give this lots of details about the project. Very, very futuristic project, very engineering intensive project, and the project that has a lot to do with how the society will probably have the benefits of this in the years to come, 10, 20, 30 years. And but lots and lots of effort is going by, by almost, as you said, half of the world population in some way or the other, the countries involved in. And a lot of money, of course, is also involved, but a cause which is as fundamental as energy, which is obviously the most important commodity for all of us, and more so in future. So let us also, on behalf of all of us, wish the IPR and the complete ITER-India group for their for outstanding contributions, and also for their future work in this project. So thank you, Ujjwal, once again.
Thank you. Thank you. With your best wishes, I am sure that we'll succeed in ITER.
Thank you. Thank you so much. And thank you all of you for joining this evening. And lots of participants have joined today on YouTube. So please come back and again join for future talks as well, which will be equally interesting. Thank you. Thank you very much.
Thank you all. Thank you, Satya.
Thank you very much for informative talk. Thank you.
Thank you. Thank you.